Okay, now I want to do the backward proof. So this is going to be the proof of converse part of channel coding theorem. Okay, this is a precursor to the converse proof. We will talk about zero error code first. So in the case of zero error code, you can show that the code rate R should be less than y equal to C. Okay, so this is the precursor to the converse proof of the channel coding theorem. What we need to show is if probability of error is 0 exactly, then rate has to be less than or equal to C. That's what we need to prove. So this is the statement that we need to prove. So this statement need to be proved. Okay, so we will start using NR, which is the log 2 of size of the message set. So that is equal to NR. Okay, so that is the number of message bits that you are sending over the channel per channel code. Okay, so if you send a channel code over the channel, you are sending this many message bits sent over the channel. Okay, so that is the number of message bits that you are sending using code per vector channel use. Okay, so NR is equal to entropy of selection random variable W. Since W is a random variable from the message set, which is W script, right? And this, you will select an index I, right? That's what this random variable is. So entropy of equiprobable selection random variable W should be what? Log 2 of size of the message set, which is script W. So that is nothing but NR. Okay, so that's that equality from the definition of selection random variable W. And I have another equality right here. This is based on the definition of mutual information. So mutual information between W and YN is equal to HW minus HW given YN. So that is based on the definition of mutual information. Mutual information. This is due to the definition of W, random variable W. Okay, so that equality is well explained. Now, let's consider the first item, this one, entropy of W given Yn. And we say that the condition here is probability of error is 0. That means whenever you received yn, you can determine w exactly with no error. That means there is no uncertainty on w receiving yn. So this goes down to 0. Okay, so all that is left is this mutual information part. And then we can use data processing inequality so that this is equal less than or equal to mutual information between xn and yn. Recall that we have this relation. Let's say w selected, then you do the encoding, then you send xn, then you send over the channel, which is defined by this. Remember this picture, right? And you do the decoding, then you have w prime, right? So mutual information between these two, and mutual information between these two, mutual information between these two is greater than or equal to mutual information between w and yn. So that's the data processing inequality. Okay, so this inequality is due to that. And since you have a one-to-one mapping, basically equality can be achieved since this is one-to-one. And so this is a vector x, vector y, and then we can have upper bound this mutual information with a summation of each individual mutual information, where I is the index running from 1 to n. And using the data, discrete memoryless channel argument, we can achieve equality. Yeah. Okay, and the final step is capacity. Capacity is maximum of mutual information over the choice of input distribution px. So if you optimize it, then we can obtain C, which is the capacity. So all these inequalities has been explained. Then dividing both sides by n, we get this. Okay, so the conclusion is that for any zero error code, for all n, rate is less than or equal to C. So that's the proof of zero error codes. That's the proof of this statement. So this statement is true. Okay, so that's the zero error probability, zero error probability code. Okay, so that for zero error probability code, rate has to be less than or equal to C. So the what we have to do now is that when this one is non-zero, right? In the case of zero error code, this was exactly equal to 0, but we will use Fano's inequality. So this we will upper bound it by the Fano's inequality. The Fano's inequality goes like 1 plus PE, and so you have a non-zero probability of error, but this probability of error goes down to 0 as you increase n, the size of the vector. So this is the term that will appear right here. So 1 plus PE and NR, because this is not 0. So, and then if you go down, basically what you have left is this side n, and if you divide both sides by n, this is 1 over n, this disappear, and this is converging to 0. R is a fixed number, so the whole term goes down to 0, and what's left is R less than or equal to C. So that's basically it for the proof, converse proof